Welcome all to this session, which is going to be dedicated for describing curvilinear motion using rectangular components. Now, rectangular Cartesian coordinate axes, x, y, and z, are usually associated with three unit vectors, I, j, and k. Those unit vectors are represented in a coordinate system like this. So this is the x-axis with unit vector I pointing in that direction, and this is the j-axis or the y-axis, and finally this is the z-axis, which is the k-axis. Now, it is often convenient to describe a motion using rectangular component, and by that you need to fix a frame of reference. So for example, in this situation, if you look at this particle is moving along this path, which is a curvilinear path, and in order to describe that motion, we would need first to construct a coordinate system. So we pick an origin right here, and then we determine the x, y, and z. And then what we do, we shoot a position vector from the origin all the way to the particle. That position vector has to follow the particle as it moves along the curve. Now, the equation of this position vector is going to be r, which is equal to x as a magnitude multiplied by I as a vector, plus y as a magnitude multiplied by j as a vector, plus z as a magnitude multiplied by k as a vector. And what is important to know is that those x, y, and z can be functions of time, so they can change with time as the particle moves and the position vector itself is moving with it. Now, to start with the description of the kinematics, we need, as usual, to start with the position. So for the position vector, we already defined it. So its magnitude is going to be r, which is equal to the square root of x squared plus y squared plus z squared, which is always greater than 0, always positive. The unit vectors, which are written like this, UR, is equals to 1 over r, the magnitude, 1 over the magnitude multiplied by the vector, the position vector. And for that, what we will get the Rx component divided by the magnitude multiplied by I, plus the Ry component divided by the magnitude by J, plus Rz divided by R, and finally we put the K component. Now, in order to determine the direction, which is represented over here down in this schematic, of the position vector, we have the direction cosines, we call them, and these are angle alpha, which is mathematically represented by cosine alpha, which is equal to Rx divided by R. Then we have cosine beta, which is represented by Ry divided by R, and finally cosine gamma, which is equal to Rz divided by r. And these angles are shown clearly here. This is alpha, this is beta, and this is finally gamma. Now, let's now move on to the velocity. So, since the unit vectors I, j, and k are constant in magnitude as well as direction, the velocity vector is going to be written as a vector v is equal to the time derivative of the position vector divided by the rate of change of time, dt. And in that case, what we are going to get? We are going to get dx divided by dt multiplied by I plus dy over dt by j plus dz over dt multiplied by k. Now, which is, in another word, v can be written as, which is the dr over dt, as the magnitude vx multiplied by the unit vector I plus the magnitude vy multiplied by the unit vector j plus the magnitude vz multiplied by the unit vector k, where vx is equals to x dot, which is equals to dx over dt, and similarly vy is going to be y dot, which is dy over dt, and finally we have vz, which is equals to z dot, which is equals to dz over dt. Now, before I leave this slide, I want to emphasize on the first statement, which is this: the magnitude and the direction of the unit vectors are constant. Now, in the next session, when we talk about normal tangential system, we will see that the unit vector themselves are they are not constant in terms of direction. The direction moves, and we will get a derivative as a result of that. So I'm not going to talk about this now. So the magnitude of the velocity is equal to v, which is equal to the square root of vx square plus vy square plus vz square. Now, and here we can see that the velocity as the body, as this particle moves along this curvature, we can see that the velocity vector is written here. And what you should know is that this arrow at this point is actually tangent to the path at that point, which we agreed. Velocity is always tangent to the path. Now, finally, let's move on to the acceleration. So the acceleration is not different. It is the rate, it's the time derivative of the velocity vector, or the second derivative of the position vector r. So if we want to write that, then we will have the acceleration as a vector is equal to the derivative of the velocity vector with respect to time, which is going to give you axi plus ayj plus azk. Now, here what we have ax is equals to v dot x, which is equal to x double dot, and which is equal to dvx over dt. Similarly, ay is equals to v dot y, which is equals to y double dot, which is equal to dvy over dt. And finally, we have az, which is equal to v dot z, which is equals to z double dot, which is equal to dvz over dt. Now, back to this illustration, this figure, again, the same particle which we have moving along this curvilinear path. And if you look here, we have the acceleration vector written in a Cartesian rectangular component, I, j, and k. But the direction of the velocity vector, as you see, is not tangent to the path. Now, it could be by chance tangent, but it's not necessarily tangent to the path. As we explained before, it is actually going to be tangent to the hodograph. Now, so the magnitude of the acceleration is the square root of the squared component, ax squared plus ay squared plus az squared. Now, and this is again the comment here about the concept of the tangent. The direction of A is usually not tangent to the path of the particle, as shown over here. So if I draw the trajectory of this, it is definitely not tangent to that point, because the tangent would probably at this point be somewhere over here. Okay? Let's have this simple example. The position of a particle is described by Ra, which is equal to 2ti plus t squared minus 1j, where t is in seconds and r is in meters. And what we want is to determine the position of the point and the speed at 2 seconds. So, to start with the solution, we have been given Ra as a function of time, which is equal to 2ti plus t squared minus 1j. Now, so if we say we want this at 2 seconds, then we will get 2 multiplied by 2i plus 2 squared minus 1j, which is equals to 4i plus 3j. So this is the position in a vector notation. So the velocity of A as a function of time is dra over dt as a vector, of course, which is equal to 2i. So the time, it was actually 2t, but we took the derivative with respect to time, and we ended up with 2i plus 2tj. And similarly, if we substitute v in 2 seconds, then this is going to be 2i plus 2 multiplied by 2j, which is going to give us 2i plus 4j. So the speed or the magnitude of VA is VA, which is equal to the square root of 2 squared plus 4 squared, which is going to be 4.47 meter per second. Now let's have another example. So in this another example, we have this. At any instant, the horizontal position of the weather balloon in the figure is defined by x, which is equal to 8t feet. So this position along the x-axis is always described by x equals to 8t, where t is in second and the position is in feet. If the equation of the path is y equals to x squared divided by 10, so this is the path which the balloon is going to follow. So the balloon will start from here and then it will move all the way to here, following this path. We want to determine the distance of the balloon from the station at A, that's the station at A, when t equals to 2 seconds, and then we want to determine the magnitude and the direction of the acceleration when t equals also to 2 seconds. So let's start with the position. So for the position, so this is the position. For the position, we have x, which is equal to 8 multiplied by 2 seconds, which is equal to 16 feet. Remember, this is the equation right here. Right here. And we need to know also the y position at 2 seconds, after 2 seconds. So y is going to be equal to 16 square over 10. And this is going to be equal to 25.6 feet. So this is like the x and y component. If we want to find the magnitude, then it is equal to the square root of x squared plus y squared, which is equal to the square root of 16 squared plus 25.6 squared, and this is gonna give you 30.2 feet. Now, to determine the velocity, we need to find both x and y component, vx and vy. So vx is going to be x dot, which is going to be the time derivative of the function x, which is at. And this is going to give us 8 feet per second. So the velocity in the x direction is constant. It's not a function of time. While vy, which is y dot, is equal to the time derivative of x squared over 10. Now, this one, the derivative of this one, you need to be very careful. First, you take the derivative of x squared. So the derivative of x squared is 2x. And then you take the derivative of x with respect to time. So this is going to give you x dot. And then you would have 10. And for that, you will have 2 multiplied by x from the previous slide at 2 seconds equals to 8 multiplied by 2, which is 16. And then we have the x dot, which we already calculated. It was 8. And this one is divided by 10. So we will get this equal to 25.6 feet per second. Now, to get the magnitude, we need to square both components, which is 8 squared plus 25.6 squared, and this is going to give you 26.8 feet per second. Now, to find the direction theta of the velocity, you would have to take the inverse tangent of the y component, vy, divided by vx, which is going to be the inverse tangent of 25.6 divided by, be careful, this is 25, divided by 8. And this is going to be 72.6. The 72.6 degrees is already represented here. So from the x-axis, you measure an angle 72.6 degree, and this is the velocity vector. Clearly here that the velocity vector is going to be tangent to the path. To determine the acceleration, we would need to find again ax, which is going to be equal to x double dot, which is going to be d over dt of x dot. Now, if you remember, x dot was 8, so this is going to give us 0 acceleration because the velocity in the x direction is constant. For ay, we will get y double dot, and remember y was a function of x, so this is going to give us d over dt of the y dot. Y dot, we calculated it in the previous slide as 2x x dot divided by 10. Now here you need to do the chain rule, and for that you will get 2x dot multiplied by x dot again divided by 10 plus 2x multiplied by x double dot divided by 10. Now clearly here, since x dot is 0, then since x dot is 8, then we got x double dot as 0. So this one is actually 0. And what we will end up with, substituting 2 multiplied by x dot again divided by 10. And this is going to give us 12.8 feet per second square. Now to calculate the magnitude, we square the two components under the square root. We got ax squared plus ay squared, which is equal to 0 squared plus 12.8 squared, and this is going to give you 12.8 feet per second square. Now to find the angle, the direction of the acceleration, you take the inverse tangent of ay divided by ax, and this is going to be the inverse tangent of 12.8 over 0, which means that this is 90 degrees. And this is represented to you over here as the angle is being measured from the x-axis 90, so the direction of the acceleration is going upward. And if you remember from the sketch, the path was going somewhere in this direction. So again, the direction of the acceleration is not necessarily pointing or tangent to the direction of the path, to the path of the particle. Now, to summarize, we have expressed the kinematic quantities in terms of rectangular component of the vectors I, j, and k, and we wrote the equation of the position as this: r equals to xi yj plus zk. Then we said that the velocity vector is equal to the time derivative of the position vector, which is going to give us dx over dt I plus dy over dt j plus dz over dt k. Again, the acceleration vector is the time derivative of the velocity vector the time derivative of the velocity vector. So we will end up here with vx over dt I plus vy, the change of the velocity with respect to time, j plus dvz over dt k. And that's it. Thank you.